Alan last week mentioned a little bit about ununs and balance, so I wanted to talk a little bit about them because it can be somewhat confusing. And so, what is it? It's basically an auto transformer or a coil or a transformer. And why would we want to use it? Basically to match the antenna, the impedance of the antenna to that of the feed line and transmitter. You can also use it to change a balance system like a dipole to an unbalanced system like a coax feed line. Or you can also use it to reduce RF in the shack. Hi, Richard. Um, so, um, antenna impedances are affected by the type of antenna and most commonly the height of the antenna and also what frequency you use. So if we look at the impedance of an antenna, if you have a dipole, it's typically 50 to 75 ohms. And, there's also a question here, do I actually need to use a balun? And some people do use a balun. Other people connect the dipole directly to the feed line and don't have any problems. When you move the feed point of a dipole over to one side, so it's at the 1/3 point, you get what's known as an off-center fed dipole, and the impedance at that point is 200 ohms to 300 ohms. So here you would need a 1 to 4 balun to be able to make that antenna work. And if you have a random wire antenna or a vertical antenna, the impedance tends to be more on the low side, less than 50 ohms, but can also be higher if you have some very long antennas. So here you'd probably need to use a 1 to 9 Unun. And I've got some pictures of these coming up. And for an end-fed half wave, you're basically taking a dipole and feeding it at the end. And typically, it could be the impedance there could be anywhere from 2,000 to 3,000 ohms. So there you would definitely need an Unun to be able to match it. So you may ask the question, do I still need it if I have an antenna tuner? Before I get into the antenna tuner, probably the most important factor is the antenna height. And if we look at a dipole, and ideally you want to, if we've got the wavelength of, 1 lambda, so let's say this is 40 meters, and you want to have the antenna ideally at half lambda, which would be 20 meters. So here, the impedance would probably be around 70 ohms or so. But most people don't get the antenna high enough. So if you get lower, the impedance, it goes up to about 100. And then as you get lower to the ground, the impedance starts to drop. So that's one of the reasons you probably need to use an Unun or a good antenna tuner, because you're especially if you're operating mobile or SODA or PODA or something like that, where your antenna height is going to change all the time depending where you put up the antenna. You're going to have a change in impedance. This is probably the most important factor that affects the performance of the antenna. So, you may ask yourself, do I really need an Unun or a balun? And you may be able to get away with it. If your dipole is in a relatively good height. Most radios that have an antenna tuner internally cover like a 1 to 3 SWR range. So that is roughly 13 to 150 ohms impedance. The Elecraft, they have a better internal tuner than most, and it covers a 1 to 10 range. If you get an external antenna tuner, typically they will cover a 1 to 10 range, and this is typically 5 to 500 ohms. So you may need an or a balun to match, especially if you're going with the end fed half wave. So some of the things that you can have, depending on where you buy your Unun or balun or you make yourself, sometimes you don't know what the toroid material is. It can be either iron or ferrite. And each type has a different frequency range. Most are pretty good from like 5 to 25 megahertz, but if you're going below 5 or above 25, then you may need to make sure you have the proper toroid material. And some people that sell ununs and baluns will actually have their own toroid material. Um, that they use. So that's one thing. If you buy one, especially from overseas sources, you may not be sure what kind of toroid material you have. Usually, if you buy toroids from a commercial manufacturer, they'll be color coded. Different colors for different toroids, and you can look up from the manufacturer what the material is. Now, most of them use 22 gauge magnet wire. So there is the bad and the ugly of magnet wire. Um, Sometimes, well, there's two problems with it. One is that sometimes people have difficulty in soldering because they don't heat the connection up long enough and they don't burn off the insulation, and so they have a poor connection. So sometimes it's tough to get the insulation off, but you might need to use some sandpaper or a sharp knife to scrape it off. On the other hand, some toroids have really sharp edges, and they tend to very easily take off the insulation, and you create a short in your winding, which is not good. So you have to be careful when you're winding a toroid. Also, if you put a nick in the wire, it creates a mechanical weak point, and the wire can break off, and then it doesn't work. The next thing that you need to worry about is the power levels. And if you put in a lot of power into your toroid, and you and the toroid gets warm, you can actually change the properties of the toroid if it gets really hot. So you have to be careful you don't overheat it. Usually, this is if you're trying to put in 50 to 100 watts into a toroid. And you can also use two or more toroids stacked together. And you can also use larger wire than 22 gauge, like 14 gauge wire. And there is both an art and science to it. Some people say you need to wind it this way. Other people say it doesn't make a difference. And when you see some of the pictures, I'll point out some of the differences. And some people see a big difference. Other people don't. Um, so um, there is this website here, which I'm going to go to shortly, which shows the various types of balance. And then there's also a book out with other designs on balance. And I think, uh, let me just go to the website now. So let me just go here and see if I can bring this back here. All right. So, um, so I brought up this website because they have all the balance and ununs listed here. So one thing is a current balun or current unun, and basically it's just you taking the shielded wire and you can wrap it in a coil, or you can wrap the shielded wire around the toroid. And this is basically to eliminate any RF going back into your shack. So here is an example of one that they wound. So why? Okay. Um, that's the second here. Oops. Just, okay. You seem to have run into a little of a snag here. Oh, okay, maybe that's the second here. Um, hmm. All right, just a second here. Um, hmm. It worked earlier today, but let me just go back here and see what's going on here. Let me just stop the camera for a second and then start it up again and see what's going on here. Okay, let me just start the camera again. Okay. Um, there is a technical problem. Okay, so let me just do it the old-fashioned way now, and let me just stop doing this here because for some reason it doesn't seem to be working. I'll have to look into it. Um, oops. Okay. All right, so let's go to the old-fashioned share screen method, and let's see if it works this way. Oh, so this is your one-to-one on. Okay, it seems to work here. I don't know what happened. So these are just examples of showing them, and these they rate these up to 1 kilowatt of power. And here he does a test on his Unun. So that's the first type of Unun. You can make this a little bit more broadband by basically just using like a speaker wire to conduct a speaker wire. And here he's got 16 turns and he rates this up to 700 watts of power. And here's just some other example. This one is 200 watts. Um, so here, the toroid material comes in 140, which is basically the inside diameter of it in millimeters, and then 43 is the toroid material. So that's this toroid. So that's another 1-to-1, and now you get into well, this is actually using it as a balun. A broadband balance. So you would connect your dipole up here and then your coax down at this end. Now here is a 1-to-4 ballad, which you would use with an off-centered antenna. And so here you basically wind the around and then you make some connections. So your coax goes into 1 and 2, and then your 1-to-4 impedance comes out here for at terminals 3 and 4. And then he's combined the 1-to-1 and the 1-to-4 together, and it's got a switch in here so he could select. So this is just another design. that he's come up with. Now, the one that's of most interest. Oh, here is. Um, okay, here is the on for random wire. So it's um, 1 to 9. So here again, he wind. So basically here for these type, you have like 3 turns here and 9 turns here. So it gives a 1 to 3 ratio. And here is just some examples. And then here's another one that he's made up using 4 wires. And you can have like a 1 to 4, 1 to 9, or 1 to 16. And then here is he's made one with a switch. And then here he's got one that he's made where he's got different binding posts for different windings here. So this you would use this for a random wire antenna. And then here is the frequency response of it. So typically, with this design, the SWR is 1 to 4 or less. And the other one that he's making is this one here. So for a random wire antenna, this was actually invented by someone from Austria called Fuchs, Fuchs, and he's got a patent on this antenna. And this is the most common one that you see. And basically, what you have is you have 2 turns and then a capacitor, and you connect your coax here, and your capacitor is typically 100 to 150 picofarads, and the capacitor provides some stability. And then you start winding your toroids, and then you flip over here, and then you continue winding on this side. The reason for this flip is that if you don't do the flip here, your antenna lead comes out at this side. Some people are okay with that, but some people like the antenna wire lead to come out on the other end. That's why you have to do this flip. And some people have difficulty in counting turns. So basically, anytime the wire goes through the toroid is considered 1 turn. So if you look at the green wire, it goes through here and goes through here. So that would be 2 turns. And you can vary by varying the number of turns, you get the ratio. So if the most common one is a 1 to 49, so you have 14 turns divided by 2 is 7. So 7 squared is 49. So you get a 1 to 49 ratio. And then here are some examples of toroids, of ununs that he's made. And, there's some um, some people say that you need to have the wires spaced closely together. Other people say they should be evenly spaced apart. Here he's actually got one where he's actually twisted the 2 turns together. Some people twist the wires together here, other people don't. And then here he's actually wrapped the toroid in Teflon tape just to provide some protection when winding it, so there's no chance of scraping the wire as you wind it. So there, if you have the toroid and the wire, they're relatively easy to make. And then he's just doing some different testings of the toroids here. So that's basically it for that. So let me go back here and stop the screen share. Oh, okay. Stop the screen share and let me stop the record.